Hello, everyone. Again, my name is Jeffrey Gillan. I'm a data scientist or remote sensing scientist at the University of Arizona, also a drone pilot, and I use aerial imagery to study and manage natural resources. To give you some background on me, I've been a geospatial professional for about 15 years. I actually started my career in the Park Service many years ago, here for National Battlefield. I've been doing drones and aerial photography for about 10 years now, maybe 11. And a lot of my background is in rangeland science and management. I used to work for USDA Agricultural Research Service, Las Cruces, a place called the Coronado, experimental range. So that's really where I got into drones and aerial photography.
Jeff, I'm good. I'm sorry. Can you really project? It's hard to hear through the microphone.
Okay.
Yeah.
Louder?
Louder. Yes, thank
Let me
you.
bring this up a little higher.
Yeah. Thank you. Thank you. You just clip it to your lip, I think.
All right, I'll try to talk a little bit louder. Where was I? So yeah, I worked at Las Cruces. I've been at the U of A in Tucson since 2015. Go into my current portfolio of work. We're going to talk about most of this. I have some civil applications where I'm working with 𝐀𝐫𝐢𝐳𝐵 County to do vegetation mapping before and after the Bighorn Fire, vegetation mapping along Santa Cruz River. I had some more kind of researchy stuff. We just wrapped up a project where we used hyperspectral imagery to ID specific plant species. In this case, it was cactus. We have a project right now where we're using terrestrial LiDAR to estimate carbon stocks in forests here in the Southwest. So yeah, there's always a variety of different projects coming on and off my plate. I also teach a drone mapping course in the fall at U of A. So I'm here to talk about remote sensing for land and resource management. I'm going to focus specifically on Tucson, Arizona. That's where almost all of my work happens to be. This is not meant to be a technical presentation. I'm more just going to touch on a bunch of different applications, kind of like what Techie did. This is what we're doing. This is why we're doing it. If you guys have any more technical questions afterward, I'd be happy to. So kind of the theme of this talk, and what I found increasingly in my work, is that multi-scale observations are often needed to answer the question or solve the problem. And sometimes one scale of data just doesn't do it. So increasingly we use field measurements, manual field measurements, drone imagery, airplane imagery, airplane LiDAR, satellite imagery, all of the above. I found that more scales of information, the richer your picture of the natural resource or the land you're trying to tax. Talking about Tucson, let's get a little bit more familiar with the geography. So Tucson is in southern Arizona. This is the main metro area. It's a big place. There's nearly 1 million people that live in and around Tucson. It's surrounded by mountains, with Sky Island mountains like Santa Catalina's, Rincons, and Santa Rita's down in the south. We also have river systems, of course. Most of them are dry most of the year. Santa Cruz River, that we'll talk about later, does flow year-round, but it is a wastewater effluent stream. So there's actually quite a bit of vegetation that grows. Make that go away.
Click outside of it. Don't go away.
So we're going to show geographically where all my projects are. So we're first going to talk about a vegetation mapping project before and after the Bighorn Fire that happened in 2020. We used field measurements, drones, aerial LiDAR, and satellite imagery to do a time series of vegetation change. Then I will talk about CDO. CDO is Cañada del Oro, which is a wash that comes out of the Catalinas. And we're interested in sediment transport. So we use drones and aerial LiDAR. Then I'll talk about the Santa Cruz River. They're very interested, them being 𝐀𝐫𝐢𝐳𝐵 County is very interested in what the vegetation makeup is. So we use field measurements again, drones, aerial LiDAR, aerial imagery. Then I'll get to our hyperspectral cacti project, which is down in Santa Rita's. And we used a handheld spectral radiometer And then we scaled that up to drone imagery, airplane, hyperspace. Finally, if I had time, I might talk about how we're using terrestrial LiDAR and then hopefully drone LiDAR to estimate biomass and carbon stock trees. All right, so first project is the Bighorn Fire. So this is sponsored by Pima County Regional Flood Control District. And the question is, what are the flooding implications of massive vegetation change due to this wildfire? So my objectives were to do vegetation cover mapping from pre to post fire for the entire Santa Catalina mountain range. So then I'm going to hand that data to the hydrologists. They're going to plug it into their runoff models to see how much water is coming off the mountain and what the downstream implications are. I also collected a lot of drone imagery on the mountain, and that's being used to support ongoing field research, post-fire vegetation. Show you a nice drone video of what the top of the Catalina Mountains looks like. It's a mixed conifer forest up there. This is before the burn, a couple months. So a lot of this is different. Here is a map made by GTAC that was mentioned earlier today. So Forest Service, basically. This is a burn severity map. So this is the whole Bighorn Fire. This was June and July of 2020. You could just, everyone in the whole city of Tucson could just sit there and watch the fire burn for 2 months. Burn about 126,000 acres, so almost the whole mountain range. So it's very interesting to see how different areas had different severity. The county's very interested in kind of going watershed by watershed to see what the damage was, what the vegetation changes, what the downstream implications are. One we really focused on was upper CBO. This polygon is right here. That's at the very top of the mountain. So there was a lot of burning going on. There's a major stream coming out of it, CBO. So we focused a lot of our efforts there. So remote sensing assets. Drone, of course, use the trusty Phantom 4 RTK. I've used that a lot in the last 3 years. It has an amazing ability to fly up and down mountains. I can give it a terrain, and it does amazing flying up mountains, down canyons, whatever DEM you give it, it does great. So I made some very high resolution products, worked with mosaics, point clouds, 𝐀𝐫𝐈𝐂 models. And so the drone imagery basically had two purposes. First one was to collect training samples for satellite imagery classification. So I just go out and fly it, and it really helped me be able to identify different types of vegetation or cover types that I can't necessarily see in satellite or aerial imagery. That was one thing, provide sampling for training. And the other was just to support the plot-based fieldwork that other scientists. So airplane, we had pre and post-fire LiDAR. We had pre and post-fire aerial photography. So it's kind of a remote sensor's dream to have all this data. So I took the aerial data and I combined it with satellite imagery. It's all from Planet. I fused them together to do a vegetation classification in a time series. So from June 2019, which is a year before the fire, to June 2021, which is a year after. So how did the vegetation cover change during that time? So let's look at some of those classification products. This is a very simple classification. The dark green is alive trees and shrubs. The yellowish green is herbaceous vegetation, and the brown is everything else. Rocks, bare ground, even sparse vegetation can sometimes get put in that class. For this one, I was using C5 decision tree algorithm, very similar to random forests. It's kind of like a machine learning supervised classification scheme, and we implement that in R. Let's go a month after the fire, and I have a new class. This class, black, is dead tree and shrub. So I can now go watershed by watershed, quantify what the cover types were, how they changed over time. Pima County takes that to create what they call curve numbers, and this is about estimating runoff. So besides 2D, we also did this change detection in 3 dimensions. So what you're looking at here is a LiDAR canopy height model change from pre to post fire. We did not, we're not able to get the whole mountain. We did not have LiDAR data for the entire mountain pre. It's like you always wished you had the data before. We didn't know a massive wildfire was going to come through. But we did have about 40% of the mountain covered with pre-LiDAR. So it was interesting to do a 3-dimensional change and see where the timber was lost and where it wasn't. Show you some point clouds that I made from a drone. Family 4 RTK, AGIC. So this is a post-fire. So July of 2021, last summer. You can see all the little black twigs. Those are trees. Here's just another one. So these point clouds and orthomosaics are going to be a companion piece for field plots that occur. So they're estimating vegetation composition in very, very fine detail. So we used to go for a much bigger area. Of course, you can't get quite the detail. So put the data sets together. Hopefully, it's a bit more rich for them to describe what the composition is. All right, that's one project. Moving on. So the next one is CDO7. CDO is 𝐀𝐫𝐢𝐳𝐵 𝐸𝐿. It's the name of a wash that comes out of the Santa Catalina Mountains. They're interested in, again, Pima County, how much sediment is being transported downstream. Did this massive wildfire now create a lot more sediment downstream? So we had aerial LiDAR that was collected before the monsoon rains last year, and then I flew a drone and collected post-monsoon drone imagery. And so this is topographic change detection. We've talked about that already today. Same kind of thing. So here's just to show you some of the imagery products. This is from one little segment along CDO. On the left is a drone orthomosaic. It's about 8.5 hectares in size. Right, it's an TM that we created from the drone. So yeah, we're doing topographic difference. So we took post-fire DEM from the drone minus pixel by pixel basis. Pre-fire or pre-monsoon LiDAR DEM. Subtract the two. So now we have a visual picture and a quantitative picture of vertical change. So this product here, the colors that represent a vertical increase or vertical decrease in sediment. We're seeing lots of blue, which means that it's higher in elevation, almost up to 1.5 meters in some places. Give credit to Dr. Jennifer Gillan. She's at U of A, and she's the one who actually is trying to make sense of this. Like, okay, we have 1.5 feet of sediment. What does that mean? I don't. I'm not a hydrologist. I don't know how to do sediment science. I can survey it. She's the one who knows that. Oh, this is normal. Oh, that's a lot of sediment. So here's just another example. This is a different section of CDO. This is an orthomosaic on the left. Here's the DEM. This is a little bigger area, about 12 hectares. Here's the topographic differencing. So yeah, apparently there was quite a bit of sediment that flowed down and accumulated right there. Okay, next application, Rio Santa Cruz River. So yeah, we use field measurements, drones, airplane LiDAR. So like I said before, Santa Cruz River is a wastewater effluent stream, so it's flowing year-round. Right, we got the drone video to show you kind of what it looks like. See, there's actually green vegetation there. There's plenty of willows, tamarisk, mesquite, olive verde, kind of typical riparian dryland species. Again, sponsored by Pima County Flood Control funding. The big question is, what is the vegetation composition in this stretch of, so it's about 25-kilometer stretch. So my goal was to map vegetation of the river in as much detail as I possibly could. The implications or reasons why we're doing this is one, for restoration purposes. They're interested in identifying and removal of invasive species if possible. Tamarisk being the biggest offender. There's quite a bit of that. And they're hiring field crews to literally cut trees and see if they can remove it. We're also using this to estimate total vegetation volume in the stream bed. You know, that has implications for capacity for flood walls. The final thing that we actually found out is very useful is identifying trash. So we'll talk about that here in a little bit. But yeah, you can really identify debris and trash very well from drones. So our remote sensing assets, so we hired Cooper Aerial. They have an airplane, I do not. So they're able to collect aerial like high res RGB and LiDAR along this whole stretch. So I take their data and I'm trying to classify vegetation as best I can. We have a smaller area of interest. So this is where I collect drone imagery, did it in a time series. So I did it last summer, before monsoon, after monsoon, and then spring. So we're hoping that like a multi-temporal approach can help us identify vegetation a little bit better than just one point in time. So let's look at that drone imagery time series. So this is just one area of the Santa Cruz River. This is about 3 centimeter resolution from drone. This is July 2021. So the rains had just started when I did this. Here's September 2021. So obviously it rained. Things green now. There's this giant scour here, which is very interesting. So water comes out of the CDO, just crashes into here. So there's a whole stream bank that just got annihilated. It's a very high pressure water going through. Right, and then this was April 2022. It got dry again. So we're using all 3 of these data sets to hopefully do better than one point in time. So I'm trying to classify each of those time steps also. This is showing vegetation height. So I'm using that. You can talk about this with techie stuff. Is that it's a useful, useful characteristic to identify one type of vegetation. So I'm getting it from the LiDAR, from the airplane, and also from drones and structure motion. So my goal is to do a thematic classification. I usually start out as simply as I can. So this is just showing woody vegetation, herbaceous, and then everything's bare ground, rock. And best we can, we try to just build up species by species. So we're doing the major woody species basically: tamarisk, follow birding, steep, giant reed, desert broom, Giddings willow, acacia. So if we zoom in, this brings up a great kind of point about the complementary nature of different scales of information. So each of these circles here is a field plot. What's called a releve field plot. And so a field ecologist goes to it, identifies all the vegetation, estimates what they think the cover, proportion or percentage. I took some of that data and used it as training classification algorithms. Some of it's not going to be that useful because there's a lot of things I cannot ID from the air that you can ID very easily from person. I can't really separate. I can't identify reed grass, Johnson grass, blue panic, things like that from a drone. Even a low-flying drone, it just looks like grass. You honestly have to have the drone like this close or something to ID it a lot of times. Limitations or cannot ID for aerial imagery. It's very high resolution, and so I like to focus on the complementary nature. That the field measurements can give me very detailed information, but only in a few little sample locations. The aerial can give me a much broader view, much broader survey, but with a lot less detail. Put the two together, you have a richer data set to understand, resource to understand. final one about this project is trash. So this is the entire work, the mosaic that I did with drone. And I was just scanning around, and I ended up finding 34 car tires in and around the Santa Cruz River, just like in this little stretch here. So hopefully the county takes this and then goes out and does some removal. It's a constant problem. Time we got?
Good, you got 12 minutes.
12, okay. Okay, so next project. So we're now going to try to detect map cacti with hyperspectral imagery. And this takes us down to the Santa Rita experimental range, which is south of Tucson. Looks like this. I would call it a mesquite savanna. Yes. It has a lot of perennial grasses, and it turns very, very green in August when the rains come. So this very much has kind of a range management, dryland ecology kind of feels to study. This experimental range is it's an outdoor laboratory specifically meant for studies of dryland ecology and livestock and stuff like that. So I've done quite a bit of work down there. So this project, we're interested in how many different kinds of species can you ID with hyperspectral imagery, and cacti became one that we thought would be interesting. So our objective was to develop a hyperspectral cacti index with a handheld spectral radiometer, or an ASD, whatever they call it, and then take that spectral or that cacti index and then scale it up to drone imagery and airplane imagery. See if we can map cacti over a broader area. I don't know if anyone's ever tried to do cacti, but it looks, in normal colors, it just looks like a green plant. We found hyperspec is actually a way to distinguish them. Talk about that in a sec. So remote sensing assets, I have them fly a 𝐀𝐫𝐢𝐳𝐧𝐚 600 with a head wall NAM hyperspec sensor on it. It has 270 spectral bands. It's a hexacopter. It's I call it the mothership. When you're used to flying little phantoms, you fly this. Power. Interesting thing about the sensor, it's not a frame camera, it is a push broom sensor. So it is building up your image one line at a time. So the processing of it was not like photogrammetry. It's very, very different. And our airplane imagery is provided by NEON. So NEON is the National Ecological Observation Network. They are a National Science Foundation funded group, and they have this awesome airplane, airborne observatory that they fly all around the country. So they come to Santa Rita every year and collect hyperspectral imagery. Thank you very much. It ends up being about a 1 meter resolution. Has 426 bands, and we certainly don't use all of those. Drone has 3 centimeters. So it's like we're stepping up in scales from handheld to the drone to the airplane. All right, here we have spectral signatures. X-axis is nanometers here. It's the wavelength in nanometers. Y-axis is mean reflectance. Each of these colored lines is a different type of plant. So we're interested in identifying cactus. We found that right here at 972 nanometers, there's this very interesting dip occurring for each of the cacti species. Prickly pear, beryl, cactus, and cholla all have this dip, where everything else does not. So cactus store a lot of water in their tissue, so they absorb a lot of the light. Instead, they reflect less. So that's what this reflectance dip is right here. It only really happens in cactus. So we can use that. You can exploit it and create a cacti index. So here's what our index is. Very simple. We take 862 nanometers minus 972 divided by 862 plus 972. This might look familiar. It's the exact same thing as AGIC, only different colors. It's basically the same thing. Okay, so we take that now that we know what the index should be. let's put it on drone, let's put it on airplane, and see if we can map. So on the left is an image, and it's a red, green, blue image, but this is from the hyperspec drone. We have some cacti that have been ID'd here. It's prickly pear, shoya, beryl. Over on the right is the cacti index. You can see that the cactus does pop out. Very interesting. Yeah, it pops out. So we found that we can map it pretty well from drone. When we scale up the airplane, it still works, but we do lose some of the signal. Because now we have an area that's a meter. And so that meter pixel is capturing some cactus, maybe some bare ground or something else. And so the signal gets kind of distorted a little bit, but we found that it's still there and it still works at a meter resolution. It was very interesting to see and use this nano hyperspec and some of its limitations. See these white lines here? That's just dead data, basically. So this instrument is supposed to be sensitive from 400 to 1,000 nanometers, but in reality, it's more sensitive to like 500 to like 950 or something. So we demonstrated that the index does work, but if we were really going to do this and do it better, we need an instrument that's sensitive to something much further away, much wider than 1,000. Something like 1,500 would be great, because there's sensor drop off and it gets less sensitive as you get towards the range. Okay, how much time? Yeah, 6 minutes. I'll just quickly say, okay, so we're trying to, we're using terrestrial LiDAR. We're trying to, in an automated way, take terrestrial LiDAR point clouds, estimate the volume of them in an automated way as we can, get the volume of individual trees, add in tree ring data, so we're taking tree cores. We fuse those two data sets together. Now we can estimate the biomass or the carbon sequestration of a single tree and then do it backwards in time. So now we have this reconstructed time series of how an entire tree or entire plot of trees is packing on carbon or biomass throughout the years. Yeah, it's a lot of work. Cindy's helping me on it, and right now we're in the process of doing all the point cloud, the automation, mostly. So I'll just leave it at that. Questions? Yes.
Is any of the data available for public consumption?
Which data do you need?
The DEMs, just any other collection data?
Yeah, everything I do, either if it's published or for the county or report, all gets put in public repositories. And a lot of that is a group on campus called Cyberse. Cyberse is a cyber infrastructure. They're into how do we store, move, analyze giant amounts of data. And that's where I put all my data is on Cyberse. But in general, like the 𝐀𝐫𝐢𝐳 reports are, they're public, but I don't know how someone finds them. Exactly. There isn't some database of here's all the reports. It's kind of more up to 𝐀𝐫𝐢𝐳 County, I guess.
Specifically, I'm thinking about the data collected from your.
Yeah, I'm trying to put everything that I've ever done on GeoMator, which is a website out of Australia, and they're the best thing I've seen going, basically, of repository for drone imagery that people can just freely exchange with you. I know State Lands is talking about that. I've seen that, right?
Well, we've got our large storage together.
Okay.
So
That's my accident, because I'm.
Certainly, well, yeah. I have terabytes of drone imagery, and I love to just share with people.
we'd love to have it. Yeah.
Okay.
You have a question in the back?
Yeah, on the Santa Cruz River, Tucson been putting effluent into the river.
It's way before my time. I don't
Is
know.
there an entry point, like near downtown, or
There's at least 2 entry points. There's 2 different wastewater facilities, Agua Nueva and Tres Rios. And they're, how long have they been doing it? I guess forever. I mean,
Do you know that, do you study upstream from those entry points?
I do not. I was, they were specifically, for this project, they were interested in where the outflow is and downstream. And so they're interested in vegetation restoration and how it's useful for wildlife habitat and so
Cameras.
yeah, there's plenty of it. It creates great shade.
Have they started having significant extraction?
Yeah. Right in my study over the winter, they hired a field crew, and I came back and there's people sawing away, chopping down giant cameras.
Are you trying to observe how it may regenerate, how successful that is? Because that stuff will just come back, like trees.
I don't know. Hopefully they are.
Jeff, there's a question online. Is your vegetation classification work on the Santa Cruz published?
No, I'm right in the middle of working on it. I have to deliver the report in September, so it is not published. Give to Pima County and put all the data and everything I did on Cypress. And I don't know how people find it exactly. I'm not actually going to publish a paper. This is not an academic exercise. It's just me doing projects with the county.
Thanks. Yeah, we can follow up.
What application are you using to find the
The RTK has its own built-in screen and built-in mission plan. So, like, I think there are different versions. The version that I bought the RTK Engine 4 in 2019, like when it first hit the market, and that's what they sold me. So it's all just proprietary. It's locked down. You use this mission planner and pretty much nothing else, but it works great. It took about a year for firmware upgrades and software upgrades to get it to a point where it could do what I wanted. And I haven't updated it in like a year or something because I don't want to sit there. It works great right now. So yeah, they actually have created a pretty good product.
Jeff, are you familiar with Green Drone?
ASU?
They're NAU.
NAU.
They partner with ASU.
Okay. They presented at Fly-In at Westland.
Yes. Jacob Draper is from Green Drone. He said our salt feeder treatment on the lower Salt River has been very successful. I'm interested to compare your vegetation classification process to
Yeah, please. J. Gillan at Arizona.edu. There.
I have a little bit of a more weird question then. So, as far as I can see from Techie's presentation and your presentation, yes, remote sensing has changed with the adding more sensors in there, but it looks like we are still doing raster analysis. But are we doing, I mean, are you guys as the scientists? I am not the scientist anymore. I'm that's behind me. But I am wondering, is there any development in terms of like doing these kind of analysis on a vector base? Like, because when you read, I mean, so this is my firm belief as a person who dealt with data since the age of 19. When you convert data from one structure to another, vector to raster, raster to vector, you are losing something in there that is inherent to that data. So when you're doing that, like for the LiDAR, for example, turn that into a surface, you are losing data there. You are generalizing or aggregating, and stuff. So is any of these things can be done, I mean, or have you seen it on vector data or point cloud data?
Yes.
Yeah.
Tons and tons. Sometimes it's simpler and easier to work with raster because our tools available. It really depends on the application. But yeah, tons. The terrestrial and drone LiDAR we're doing with estimating volume trees. There's no raster. It's all points. We take point clouds, analyze the point clouds, try to estimate what the volume of the trunk is, all things like that. I did a project where we estimated forage utilization from grazing cattle, doing a kind of a pre and post kind of change detection. It's all point cloud based to tell you what the vertical change of grass is. All point clouds. You know, so yeah, there's tons of point cloud analysis and tools.
Thank you. Thank you, Chef. Anybody else?
Yes.
Last, Taylor?
So, like,
Yeah. So I am using LiDAR intensity as a characteristic or variable in my classification along the Santa Cruz River. I don't have a whole lot of knowledge or experience on how consistent it is. You know, just kind of anecdotally looking at. Sometimes it makes sense to me, sometimes it doesn't. I usually throw it in. So yeah. So for those who don't know, intensity is basically the reflected strength of the LiDAR pulse. And that's just, you know, another piece of information because different services are going to have different
variables having that on the intensity too.
right.
So one last question. Are the data from your camera easily converted to reflectance, radiance, /radiance, or is there a process for that too?
Okay, most of the drone stuff I do is not radiometrically correct. I did that in the past, multispectral. I still do it sometimes. Use a panel to get to reflect this kind of stuff. I have found that for my applications, it's not very necessary. I'm usually not interested in spectral signature. I'm usually interested in its shape, size, and then maybe what it is. In that case, it's just red, green, blue, radiometric calibrated has proven to works just fine. So no, I have not done a lot of that, and no, my drone imagery cannot really be converted to that. It was never set up to be radiometrically correct.